So we start with the last talk today. The last speaker, I guess you know him, is Professor Nassim Taleb. Is a professor at the American University in Beirut, and also linked to Universal Investments. Is the author of The Black Swan, Anti-Fragility, Full Band Randomness, and many academic papers. We have been knowing each other for a few years now. We have been working together. We will for sure tell you that I complain about restaurants, so I already spoiled that. And that's it. So, Nassim, the floor is yours.
You know, I know a few things that Professor Cirillo is non grata in upstate New York, here where I live, actually in the suburbs of New York City. He insulted he don't insult restaurant owners by telling them that their food isn't great in New York City.
Because he was pretending to cook Italian food, and
I know that they are, they're Sicilian. Let me tell you. So it was very dangerous to be friend of them. So let me start with Peter, because I guess it's about Peter. So my conversation with Peter over 26 years. So I guess Dilip has known Peter for about the same period of time. Dilip, no?
Yeah.
So, that was my last meal with Peter. He ate everything. That was I think that was a pseudo-Italian restaurant. It was actually bad, not like the other one. It was actually bad. In Brooklyn, near his house, and that was a tiramisu, and he ate it all actually. Okay, he ate so fast because he eats fast.
He eats fast, yeah.
I didn't have a chance to have a bite of the tiramisu we're supposed to share. Okay, so and that was the last conversation with Peter about I don't remember exactly what, but it was right before. I mean, just like you, I had some unanswered questions that would remain, I guess, unanswered. And so, but let me tell you one thing I've known about Peter. You see people who are mathematicians, you meet them, and then 20 years later, they're in the same place, maybe degraded a little bit in their knowledge and more focused. Peter, it's like his life's like a ladder. Every 6 months, he's a new person. No, you notice mathematically he started off as an accountant, and progressively became a mathematician. So I saw that the fellow at 60 years old was still like growing at the speed of a 19-year-old undergraduate student. So that's one thing that struck me about Peter. Quite inspiring. Another thing that I discovered that Peter was Maltese. He changed name from Caruana to Carr. I guess he's Canadian. Nobody's perfect. So he had to. So that was, and I discovered one thing that I didn't know, that I could understand him. He could speak Maltese to me. As a Lebanese, you can understand Maltese like 100%, particularly if you know Italian. But he couldn't understand me. So it's not symmetric. So he discovered something that Peter understood, that the Kullback-Leibniz divergence, right, is not symmetric as a measure of distance between languages. So, okay, so rest in peace. So now the talk today. I guess everybody's familiar with this kind of stuff on the web. Fellow please, where you can link the associate degrees awarded in emergency medical tech and Miss America's age. There's a lot of things you can link, okay? You can link how many people diagnosed with syphilis, and the number of how many new securities were created on Wall Street that year. You can. So there's a lot of associations that we know. It's not like correlation is not causation. In this case, it's worse. Correlation is not correlation. So what is the problem? The problem is that correlation is a stochastic variable. And that's something I tried to explain in the first volume of the insert of dynamic hedging, published in 2001. My whole thing is that everything, I mean, people think that correlation is a fixed variable, okay, and then you have two stochastic variables. No, correlation is a stochastic variable. Particularly, okay, it becomes less stochastic when if okay, you have a proper distribution and n is very large. So there's worse. Here I have two entirely random x and y, and you can create regressions. But visibly, we have ways to control for that. In the case of correlation, you have square root of n, and here it's a little more sophisticated. We'll see how. But the regression, people take it for granted, and of course, what this topic is going to be about is pulling the exact distribution of, if you hack, in other words, how many did we have here? Uno, due, tre, quattro, nove, 3 by 3. So we have the maximum of 9, the maximum absolute value of 9, the extreme of 9 correlation, okay, or 9 regression slopes, which maps to the same, in a simplified world, visibly, and then you publish a paper, 9 trials. Okay, so this is sort of like what you wanted to investigate here and generalize with something exact. So now there is, I don't know if you're aware of, in social science, there's something called the replication crisis, in the sense that you would think that a certain number of papers don't replicate in social science. In fact, the majority of psychology papers don't replicate. I'm not talking about economics yet, because economics has dimensionality problems they don't have. So the great majority, you read something that doesn't replicate. There was a paper on sort of like, that's a team of pulled by randomness by fellow and Professor Cirillo, and I had a fight with him. I don't know if you know that we had a fight with him. We had a back and forth during COVID because he doesn't understand fat tails. But he wrote a paper on, this is the most cited paper in science. 2005, Ioannidis. And then we had a debate with him, of course, 2020 during COVID, on why most research findings are false. So I had written, after pulled by randomness, a bunch of technical stuff that I didn't know was and so what I did is, it turned out, and this is the basis of the paper I'm writing, I'm going to map to the top, is what I'm writing here is I looked at, I asked ChatGPT, I discovered ChatGPT as also a means for entertainment if you're bored or something. And or if you have a boring neighbor on a plane wants to talk to you, so you get busy. But so I discovered that paper I wrote in 2016, ChatGPT, is a consequential one on pulling the exact distribution of p-values. Okay, why am I talking about this? Well, it so happens that people don't know that p-values are stochastic. P-values are, in other words, I have the same, I generate by Monte Carlo the same experiment. In other words, what is p-value? Is you take, mu minus, let's take one-tailed p-value, mu minus something, okay, divided by sigma square root of n, okay, by square root of n, and then you compare that to the control, and the control distribution, and you see what is the tail you get using the control distribution. So people think that, hey, you know what? The n doesn't appear in the p-value. Okay, that n disappears because it's both in the control and the other one. Is how many sigmas distance intuitively using the other distribution. It doesn't appear, so people don't realize it's stochastic. So I didn't realize the importance of that 2016 paper till ChatGPT helped me, because I was very lazy. I'm going to see how I asked ChatGPT to explain to me my paper and explain to me my derivation, because I don't know if you realize, but after 9 years, your notation, you can't understand your notation. You got to go, and then of course, if you're sloppy with the way you present things in a paper, okay, you're not going to understand your own paper immediately. It's going to take a while. So why make that investment? ChatGPT did it for me. But look here. This is the Monte Carlo, and then have the exact distribution mapping to it of what happened if you have a true mean of 0.12, a true p-value of 0.12. Because of the skewness, this works. No, this doesn't work, does it?
No.
Okay, so 53% of the realizations of that random variable would be below 0.05. Crazy, The true p-value is 0.12. It means you don't have to do anything, okay? And you have a high probability. You have 53% probability of having a paper off of a non-paper, just on the first trial. And then you continue, of course, the median, the cut point is 5%, okay? But you realize 25% of realization will have a p-value below 0.01. So what happened is that, so this paper, 2016, set on arXiv, and I was invited to pay a whole edition, to write a whole edition of the American Statistician. They were doing the debate on replication crisis, and invited to submit it. But then the problem is neither referee nor the editor could understand the point, because they're all psychologists. So, and the psychologists are very nice people socially, but not dealing with something serious like this. Okay, the p-value. So the problem is that they couldn't realize the p-value is stochastic. Say, well, no, it's not. This is a random variable. They couldn't get it. It's a random variable. Same ensemble. If you repeat it, we in finance understand that. You generate by Monte Carlo something, and then you get different results. Like you generate two X and Y, and they're correlated at 25%. You're going to observe sometimes 10%, sometimes -5%, and sometimes 70%. Okay, we understand that, but they couldn't understand that notion of ensemble.
Their data is unique.
That's the point, exactly. Their data is unique. So now I ask. I was able to pull in 2016 the exact distribution of the p-value. And you know what happens? We do deal with extreme value theory. Once you know distribution of something, it is trivial to get the expected maximum based on n trials. Okay, so I got this. So this is complicated, but then I went to ChatGPT. Okay, key insights for Taleb's paper explained to me that beta distribution of p-value, modeling p-hacking via minimum p-value selection, implication for statistical significance and reducibility. So basically, it explained my paper and why it was important. I realized, it is more important than I wanted. So let me show you exactly the steps I followed in the unreadable part that I showed you earlier. T is a variable that follows a student T distribution, but basically whose degrees of freedom is n, all right? Because so the distance from in sigma, okay, from the thing, and then this is the p-value. And what I did is I changed variable, and I did the distribution of the p-value off of the distribution of the primary variable. That's it, okay. And then when you have under 30, n is under 30, use student T. Beyond that, you normalize. Okay, so with normalizing, we got a I'm going backwards. By normalizing for large n, you get a much cleaner distribution than the other one. Okay, that's it. So the point is, it's not important. All that the derivations are not important. ChatGPT gets it. What is important here is that people before used Bonferroni for multiple testing, and Bonferroni it's a fudge that's not fun. It's not good. All right. Here is explained why your framework is stronger. ChatGPT telling me when I'm sitting here. Why your framework, your meta-distribution gives the exact law of the minimum across n trials, not just an inequality. Bonferroni is conservative. Your derivation shows how distribution p-value is skewed and how p-hacking rapidly drives effective minima far below 0.05. That's what Bonferroni says, divide the values up. Basically, it's writing the paper for me. The summary is you start with it, whatever. So this is a result. Look, one thing shocking about p-value. Number one, it's very stochastic. And you know, the more stochastic something is, the more you're going to have the extreme your extreme is going to be. You see, like if you try 4, the more you're likely to get one that diverges from the rest. So if your underlying end, okay, in the experiment is 5, 15, I did that for, of course, for the Gaussian case. But look how your p-value is for 0.22. You already are likely to get from the first experiment the p-value of half of that. If your true p-value is, because the distribution is skewed. So you got a lot of small numbers and one p-value that's high to compensate to get on average 22, the true p-value. And sorry, no, what's happening here? If your true p-value is, and look how quickly, in how many trials you get to below 1%. It doesn't take a lot. So basically, in 4 trials, you're already within guaranteed statistical significance on something that is absolutely rejectable on its own. Okay. Now, what I'm saying may be trivial to anyone of them. It's actually trivial to ChatGPT, trivial to anyone. But nobody gets it. They have p-value debates using words and words and words by people whose second language is English and fifth language is mathematics. That's the problem, right? So that's what we're getting now with p-value, okay? Hackable, and we know exactly how hackable it is. It hacks very quickly. Next, regression. Regression is less hackable. So in other words, when you do regression and your true, say, R squared is 0.1, you get, this is purely random, your R squared is 0. And your n is 50, you get an R squared of 12 laboriously. You need 50 trials. N is the number of trials, you see? But it's still, I mean, if you still, in other words, out of so many papers, you can say out of 50 papers, one of them is bogus, okay? You can already say that with a regression. So regression isn't as impressive as p-values. So in other words, this is why people like p-values, because you can game it. Regression is gameable, but not that gameable, okay? Now we're going to see later why these small numbers don't have any significance because of the misinterpretation of correlation, okay? So I'll continue now. Now, finally, we're going to talk about higher dimensions. There's a problem we have in finance, and that's a severe problem in finance that they don't have elsewhere. As Dilip mentioned, they live in a finite small little thing, and we have a lot of variables. The problem we have is a large D, small n problem, okay? How many variables do we have today in finance? We have something like 50,000 random variables, clean random variables, okay? What is, it gives you a correlation matrix of how many correlation? 50,000 by 50,000, all right? Take about half, is it? N minus 1 half. So that's about a lot, okay? So we have a few billion correlations in finance. Now the thing is, what compensates? It's the same, the similar distribution as the one I did for the regression. What compensates for the fact that you have a lot of dimension is having a lot of n. You see, the first slide I showed is because the n is 20. With an n of 20, you have dimensionality. You can, but if the n required is 2,000, okay, of course it's going to wash out. because it goes down pretty much the square root of n. Okay. So the problem we have in finance is every time you introduce a new security, okay, you have 50,000 new correlations. Okay. For every new security, you're adding correlation. And then to compensate, you need to add more data per security. So every time you introduce new security, you got to go another 5,000 years back for all of them. And I don't know, we weren't trading 5,000 years ago. We were even trading 5 years ago. Right? I mean, I remember when I was trading, when I had hair and I was trading, we didn't have as many securities. We probably had 5,000 securities. So that is what was happening here. Okay, so Tracy William. So there is a way to figure out all that, and I didn't invent anything. And it's pretty much the Tracy William statistic. And for some weird reason, it's only Italians who seem to be interested in it because of the approximation coming from the Italian guys. And so I used one to get the distribution of the maximum. The point is, when you do PCA, principal components, okay, it is a random variable, right? The leading eigenvalue is what the Tracy William does. It gives you a distribution of leading eigenvalue. So you know under the null hypothesis what it should be. And now the point is it gameable? Of course, it is highly gameable. But the Tracy William, which is not really often used, is supposed to control for that tension between n and d. So it penalizes you very heavily when you add an n, when you add a d. So to repeat, we have this is a correlation matrix. Okay, we have this is a d, x1 through xd. Okay, so we have here how many correlation do we have? Possible correlation. And every time I add a correlation, I need to compensate by having a lot more n for all of them. And that shows in the Tracy William, okay, the leading eigenvalue of your, when you do the dimensional reduction. So I did figure out how many trials, and in 4 trials, in other words, you have an ensemble, say with 10,000 securities or whatever, the n securities, you do your PCA. Given the wealth of securities, you redo it on some other, you cheat with it. And that's the effective dimensionality, how it shows in Tracy William. Then when I figured out distribution of the maximum for M trial, the maximum, fake Tracy William you get from N trials. And here it does climb quite quickly. So even with the controls we have over dimensionality, giving you fake results, you can still gain because you can pick other securities. Because you have a choice by taking the maximum of a lot of things. So let me continue to give you sort of like intuition of that. So this is in my book on fat tails. I show something simple here. This is, if I do a PCA and I rank the eigenvalue, and my n is 30, okay, look what I get. I get these all fake because it's completely uncorrelated random Gaussian random variable. And under both here, the uncorrelated and independent, which is a rare case in that environment. You get this is a fake 0.2, okay, for that. Okay, that's in a Gaussian world. And if I go down to 100 securities, look, the highest fake is 0.6. We've taken already the leading eigenvalue, which is the maximum, and that's included in Tracy William. But that's in the Gaussian world upstairs. Okay. Now I wrote a book on the consequence of the fat tails. It's not a book; it's a collection of papers. And I think Professor Cirillo, we have at least 3 papers. You have 3 papers in that one out of 32, whatever, in that book. We have if we are dealing with fat tails, and guess what? Finance is all fat tails. Okay. and I know it's fat tail because I exist. You know, that's all I do for a living is hunt for large deviations. Okay, is so if you know fat tails, look at this. The spurious correlation, in other words, the highest eigenvalue is going to be to the moon. You're going to have always one because of fat tail. It's sort of like dealing with it resembles the inequality you observe in wealth because wealth is fat tails. Okay, versus inequalities we have in Gaussian. So in other words, if you collect people in Winterthur, you collect them and weigh them. You know, you're not going to have, and then add a sample very, very quickly. You see that they're not going to be too divergent. But if you take the wealth and you have some of the wealthy people from Zug in town to lecture, okay, then suddenly, you know, you can have like, it's sort of like have the equivalent of someone who weighs 5,000 tons, okay, walking in, that kind of stuff. So that kind of stuff, we see it with dimensionality. So given that in finance, okay, we have a lot of securities. It is highly gameable. You can even game the Tracy with them. You can, because of fat tails, you're going to be, you're going to be completely taken advantage of. So any covariance matrix that people say, oh, assuming correlation worked, they don't. Okay, and assuming they were stable, they're not. And assuming we had the conditions, you know, for them to allow you to build a portfolio, we don't have these conditions. We don't have ellipticality. Assuming we had all of this, okay, we still would have a problem of people gaming it by giving you the correlation matrix that they want. Okay, and that's part of Tracy with it. But because we're in the fat-tailed world, it's a lot worse. So I dealt with three cases here. P-values, which is the strongest and the most consequential. I don't know, did any one of you take any medicine the last 5 years? It's based on some p-value, all right? And then they tell you later on it doesn't work, all right? So, I mean, based on p-values, all right? I mean, of course, by practice, people start dropping dead and stuff like that, and of course, you know it doesn't work. And then they say, well, something about it we didn't see. The thing is gained. You have to have a p-value of at least 2 orders of magnitude worse for it not to be gained. So we saw p-value, we saw correlation, not that, regression and correlation, it's the same distribution actually. Not that big deal. Dimensionality, very serious big deal. With a Tracy Wyndham, allowing you to go to, you can easily go to 10, with 10 trials, you can go to 1.6 sigmas. Okay. So since I still have a little bit of time, I'm going to continue with more issues. And because that's not part of this is part of the paper, not part of the other paper, parts of the paper I'm writing, a problem with interpretation of correlation. A lot of people have problems with correlation.
But if I eat and like it, I don't care about the p-value.
No, but if you don't drop dead, yes, of course. That's the idea. Conditional on you have a survivorship bias. Yeah. The point about p-value, I think that what Peter Carr said that, no?
I don't know.
Peter said something to that effect about if I eat it and like it. Yeah,
I see.
Yeah.
Okay.
Peter had a joke like that. So here I have a bivariate Gaussian distribution, and I'm spacing these iso densities. Okay, they're all the same by correlation. I'm spacing them by correlation. So in other words, you have the same distance vertically, horizontally, diagonally, diagonally, right? So what do you notice here? The correlation 0.5 is closer to 1 or 0. The correlation at 0.8, 0.875 is closer actually to 0 than it is to 1. So we see nonlinearity in this. You can eyeball it with a Monte Carlo you generate. You can eyeball it visually. Okay. So now we realize that you shall not interpret correlation linearly. That's the first statement I got for that. And some people say, well, we're remedying it. We're taking squared correlation, like the R square or square, whatever people square something. You're not solving any problem. Now, how do you solve the problem? Is there any trader in the room? Okay, discover that from the back road of the Kelly criterion. Okay, how much do I bet on horse B knowing the performance of horse A? Mutual information. That's entropy. Okay. If you use entropy, guess what? Look now. Of the visual maps a number. No, the distance between the distance between no, sorry, there's a correlation problem with this. With my okay, the distance. Look at it. They're equidistant. No, visually, and that's mutual information. So in other words, if you start doing things dynamically by saying not what's the connection between us, but if I keep investing, it's not a one-shot deal. I get this. So mutual information is pretty much the sort of the joint entropy of two random variable, not the cross entropy, the joint entropy. Now, if you use mutual information, vastly more informative, assuming you're in Gaussian world though. If you're not in Gaussian world, it still works, unlike correlation. But it's more complicated. So in the Gaussian world, you must use distance things and allocate based on mutual information. Makes vastly more sense. I think some people have discussed it, including the great person in the government, Kelly criterion. Thorpe. Yeah, I mean, this is very natural. I did that for genetic distance, whereas previously, when they do genetic distance, it was using correlation, and did that in a paper that was accepted. You know, so I can't discuss the paper that was accepted. I can talk about. I suppose here, otherwise, Peter would have let me talk about papers you're writing, right? Not papers. But I'm continuing on this with the application of this idea of mutual information to other things outside genetics. That was in a genetics paper. So it looks like I think I'm done. I'm done. Okay. So I mean, there are other things, but let's focus. So let me summarize very quickly what I did. We started something as trivial as p-values, discussed everywhere, and people know there's a problem with it, including Ioannidis, but it's all like romantic stories, filling out pages, not figuring out. But the point is that it is a realization of a process is not the process itself. Okay, so that's very simple. We in finance understand that. And given that I'm in finance, I don't have to work hard. I'm in finance to just apply it to p-values and realize that all this debate is nonsense. The p-values are random, same as correlation, it's a random variable, same as whatever you want. Even Tracy Whitman is a random variable. So the second thing is, if it's a random variable, then you can game it. How do you game it? By taking the maximum of 3 observations. You know that as option trading. Okay. You see, you have optionality by gaming, and then also not telling people you're gaming the system. So this explains simply why a lot of innocent people didn't cheat with their data. Like they say, well, a lot of the replication crisis was interpreted as the person cheated with the data.
By replication crisis, you mean people not being able to reproduce the paper?
Exactly. They do it with some other cohort, and they discover other results. You see, and they say, well, the guy cheated. I mean, some people cheat, okay, and we know who they are, but cheat locally, and some people cheat globally, whatever. But they're more likely gaming the system than cheating on the experiment or lying. Cheating means strictly violating the rules of the local rules of the experiment, where you're not supposed to change the numbers or reject the numbers that you have. So they don't have to do that to have a paper that looks great and then not be reproducible. So, and then I explained why in finance we have a bigger problem. But in finance, nobody takes correlation seriously. So we already know that, and nobody takes really these things seriously for allocation, the financial interest. So I think I'm pretty much done. Say stop, so we can move to Q&A. Thank you for listening.
Questions? Please.
Honestly, does the distribution change of the p-value depending on the underlying test that you're doing, or the variable you're testing is integral pattern? I mean, is it
technically no. No, technically no, because you're betting on probability, and probability is not fat tail. The distribution of probability is it's between 0 and 1, so it cannot be fat tail. So for example, if I take a random variable that's very fat tail, okay, the survival function, which is what you're dealing with, of the random variable will not be unconditionally, it's actually uniform. You see, there's a theorem on what's called the uniform, whatever the.
Probability integral.
Sorry?
The probability integral theorem.
Yeah, the probability integral theorem. By that theorem, basically, if you know nothing, it's uniform. And then if you know something, then you can debate. Bayesian will tell you that it's beta, okay? And odds are it is a beta, but I don't want to get to that debate. So probability itself is, that's the beauty of it, is just like correlations, they're bounded. So when they're bounded, they're going to be thin-tailed distribution. Maybe not Gaussian exactly, but thin-tailed enough.
But there's Keynes' story, right? That he says that if you don't know something, then you don't know arbitrary transformations of it either. And so the p-value may lie between 0 and 1, but I could take his logarithm and I would be in a wider range, and then I'd get some tails out of it.
Yeah, but the thing is, it's exactly the reverse of the pseudo-optimization of something. The problem is when you do a transformation of random variable, when you transform a random variable, say I'm in a 0-1 space, I transform it to log space, or I do something, I can fatten the tail or thinner the tail. My conclusion only applies to that transformed variable, not to the original one. You see, so for example, if I take something that's very fat tail and log, it's going to be thin tail. Okay, if I square it, something will be even more fat tail. So my conclusion that I'm getting only apply to that transformed variable. And there's something very interesting, by the way, that is very interesting. Let me bring this paradox since we're here, and because actually we put it in our paper, we put that paradox, but your entities couldn't even get p-values, so you couldn't get that that point. If x, the number of people, if the rate of growth, okay, the rate of growth of COVID, okay, is fat-tailed, okay, is Gaussian, okay, if R is Gaussian, okay, then x, the exponential of R is going to be log normal, no? You agree? If this is slightly fatter tail than Gaussian, this is number of people killed. Number of people killed. The number of people killed will be fat-tailed, unpredictable. Whereas the rate of growth is thin-tailed and predictable. Okay, if it's more than Gaussian, this becomes power law. Okay, so it becomes fat-tailed. So we know the exponential always fatter-tailed than this one, and even log normal at high variance would be fat-tailed. But the point is, why? Because the small error on this, okay, blows up here. So this is predictable. And the guy said, well, I can predict the growth rate. I said, predicting the growth rate is simple. Predicting the function of the growth rate, which is how many people will die, all right, is a different business. They can get it. And so we put it in the paper insultingly, not the other. Okay, I mean, dealing with the author of the highest cited paper ever in science. Okay, our debate was with him. He said, "Oh, to be a science, you need to predict the number of people who die and stuff like that." And the gross, he confused. And then on Twitter, I don't know if you know, but there are a lot of insulting comments on Twitter. For those who enjoy Twitter fights. Okay, anyway, so this is interesting. Now, this applies to probability. Okay, this is why in finance, CVAR may work. Okay, but VAR may not work. Sorry, VAR may work, but CVAR may not work because value at risk is about the probability. Okay, the other one's about a payoff. So you can predict. This is the reason why betting markets don't map to the real world, because the probability, you can get the probability right. The payoff is more stochastic. Same problem as here. So this duality between P and a function of P, which is the payoff, this duality is such that if you transformation actually worse than anything they worsen. You're cheating by transforming this into this, and you're cheating by transforming this into that. This is why each one is a different animal on its own, because they have a different class of error. Because the class of errors here, if this is exponential, or thicker tail than exponential, okay, slightly thicker tail than exponential, this would be the power law class. So, okay, so sorry for the digression, but it's an important one.
So the solution, if we were at the FDA, would be just repeat the test 1,000 times and try to find what is the true value? Or like how can you get out of it?
Everybody knows it doesn't work. P-value doesn't work. So, and I think the solution is to have, because physicists, they sometimes produce p-value and nobody complains in physics. Why? Because you look at their p-values, 10 to the minus 7, right? Okay. And they tell you, when you tell them you got to get something in that class, to psychologists say, well, look, I cannot write papers, I got to make a living. I said, go make a living, go drive Uber. You can make a living, become an electrician. A lot of people, can do something a lot more honest than just publishing papers, because that's what they want to do. So that's the problem, is that you have to have a much more stringent. Now in medicine, what happens with that is that medicine is very extreme, because we started publishing, fighting with doctors, and the best way to figure out medicine is to fight with doctors. Then you figure out their limit of how they think. The way it works is because doctors hate one another. So they're going to be, you say something with a p-value, some other guy will tell you, no, fat works, and then give you some other stuff. So, and then people do meta-analysis, where in meta-analysis, you're going to have the one that win is the correct argument. So this is why, why would you need a meta-analysis? Analyzing 72 papers. For blood pressure, 72 papers. Why on earth do you need 72 papers? One should suffice, no? If there's, so they sort of like deal with it but they have other problems, statistical problem in medicine visibly, but and of course particularly in epidemiology, because they don't know about fat tails yet in epidemiology. So Pasquale and I wrote a paper, the first paper in Nature Physics on pandemics. Pandemics are very fat-tailed. They don't have, and they have no property that's tractable, except that their arrival rate is measureless. So we wrote a paper on wars and pandemics. It was exactly the same paper, just changed the data. Okay, it was very similar to wars. But up till now, it's not till like last week that I got a call from the CDC in Atlanta, but someone who said, can you try to tell us more about this fat tail business? This is the fat tail variable using, it's now that, it's 100 some years after the Spanish flu that you're waking up, that maybe it's the fat tail thing.
So effectively, every study is a realization about the correct value.
Exactly, unless your N is very large. Now, let me tell you the good thing in medicine. You read papers coming out of China. Okay, guess what N they get? 4 million. 4 million. They recruit 4 million people in a cardiology study. not like N of 71 or well, there's a recent paper on optimal level of LDL in China. They had an N of 4 million. The recruiters. So this is why China now has 20% of nature index and going up because they had their N is monstrous. And people are obedient. In other words, you're not going to say no. Sorry, I have.
This is the N of a number of papers.
No, it's the N. It was in a paper.
Oh, that
when
was in
the
the
paper had 4 million, it's so ungameable. That's what they're doing in China. With there was a very interesting thing on LDL, where they showed across a lot of all-cause mortality, all this good stuff, primary prevention stuff like that. LDL. And then I showed it to a doctor. He said, "Well, they're coming out of China. It only works for Chinese." Say, "You're ignoring the center, 4 million." Okay, how potent that is? They don't realize how potent that is. You don't need to do a meta-analysis. So anyway, assuming nobody cheated, or there's no bias and there's no, of course, confounders and stuff like that. The N of 4 million will give you. So the LDL, the optimal LDL, they showed is something around 120. Even for secondary prevention, it's not that low. Because so you realize that you're by lowering your LDL, your all-cause mortality goes up.
Why so?
Sorry?
Why so?
Visibly, if God or nature, I don't know your theology, but it gave you an LDL on average of 120 or 115, and you lower it to 50 because someone listened to a podcast by a guy called Peter Atiyah, or you lower it to 50. Well, visibly, if nature wanted you at 50, it would have given you a 50 LDL. Okay. Plus, there are other problems with cholesterol. That there's a base rate fallacy. Something as trivial as a base rate fallacy that even psychologists discovered, okay, is missing in the cholesterol studies. How? Okay, very simply, if they go by LDL, which is unconditional, all right? Now, there's something called LPA. 23% of the people have high LPA. Now, these have a genetic predisposition to have a heart problem, okay? If you're LPA negative, then your mortality rate should be different, no? If you're conditioned on LPA positive or negative. And so I went and they couldn't figure it out, okay? They said, well, I'll talk to my statistician. So that's a base rate fallacy. In other words, if you're negative on something, then that set of data doesn't apply to you. And we know exactly how. So pretty much like 15% over, the bias is 15% higher in LDL if you're LPA negative for the same effect. Other questions? So this will be a paper. You could probably, if you still remember me, you can Google it in a few weeks and it'll be a paper, this one. The p-value part of it is the meta-distribution has been on the web since 2016. So actually since 2015. The one on correlation, that these graphs I showed you, will be in a paper soon if I...
Replicatable?
Sorry. The problem in the summer is the bicycling season. So when it starts, getting cold for bicycling, then I'll start producing papers. I guess we'll take more questions or.
Other questions?
Yes.
Your elliptical graphic of all the different.
Yes.
Reminded me of a well-known phenomenon that if you take the deciles of two variables, the correlation tends to go up on the top decile, and even though the correlation of the entire population ought to be the same, if you scale,
okay. So let me tell you, this is another bias. Let me show you this bias. Actually, it's in this part. It's a slide I skipped. Let me show it to you. Correlation is sub-additive in absolute value. Okay, and let me show you.
Can you quantify that
Yes.
so that you can make a prediction about how much the correlation is going to go up.
Yes, you can do that in closed form, not closed form or computable form. So let me show this problem I didn't discuss before. If I take 4 quadrants, okay, I have this is positive, this x and y, okay, x positive, x negative. Okay, so if I just take the negatives on those, all right, I get a correlation of 0.52. If I take the negative positive is 0.18, and if I take the positive 0.52. Now you realize they're not additive. They don't add up, which means your sub-selection, if you sub-select from the stuff, you define a different correlation than if you don't sub-select. So in other words, I have a population, all right, of people who don't have whatever.
I mean, if you select enough, you'll get perfect everywhere.
I get what?
If you select enough, you're going to get perfect everywhere.
Yeah, but here in this case, if I sub-select I get a non-additive. It's not additive, right?
No.
Yeah. So mutual information is additive. Correlation is not additive. Why? The reason is because you're changing the mean when you sub-select. You see? So when you sub-select, you change the mean, and that causes it to be non-additive.
And there is a semi-closed form way of making that.
Yeah, you can show that semi-closed form, but you don't need to. So what happened to give those who are not were daydreaming or checking the stock market, the close or the Swiss stock market. Let's just say if I have a population, say of drivers, okay, and people who drive, people who don't drive, and then drinking and non-drinking. All right. If I sub-select from it the drivers, I get a different distribution than if I have the drivers and non-drivers, even between drivers and drinking, right? So the problem is, but that's correctable, but let me tell you, correlation is such a lousy English 19th century English eccentric Englishman idea, right? That doesn't have the sound mathematical properties of entropy that method, like mutual information or signed mutual information. In other words, whether you put positive mutual information is in the same direction or not. So this is, for example, very simple to show you where. Plus, if you have nonlinearities, then I have these weird things of take this one. The correlation is 0. That's a strategy. Correlation between x and y is 0. Here, mutual information is maximum.
Perfect on each side.
Yeah, but you know what? Mutual information is maximum. Capture that.
Yeah.
Okay. Or this one here, the classical problem, if I have piecewise correlation.
Because correlation measures linear dependence. So as soon as you don't have perfect linear dependence, then it makes no sense to use correlation. The point is that people keep on using it.
People keep using it. You should use mutual information for decision making or at least for clarity.
Flat, wherever you
I would say you should use calculus.
Sorry?
You should use calculus.
Yes.
Corpula, yeah. Copula, the Gaussian copula, no.
Especially
non-Gaussian copula.
So if you move, it's true that you can have a correlation which is very small on average from the whole sample and then becomes very strong in the tail because there is, for example, extremal tail dependence. But then that can be measured with alternative measures, not correlation. That's the point. Correlation will not be able to measure that.
I forgot, by the way, I had that question on gross following distribution. This is a new paper. I don't know if you remembered it because this is what we did with
this is the one with yes, yeah.
And then there's also the problem with the bar problem. Anyway, so I guess we can take one more question or.